Hello dear students, welcome to my lecture. In this lecture, I will be discussing energy eigenvalues of particle enclosed in one-dimensional potential box of infinite height. Let us take potential box of having two residuals A and B at x equal to 0 and at x equal to A of infinite height, and let us consider a particle of mass m enclosed in this potential well, and it is allowed to move only along the x-axis, and here there is no force acts on this particle. When this particle collides any one of the rigid walls of the potential well, then only that force will be exerted by these walls on this particular particle. So the force exerted by these walls can be defined as F equal to dou v by dou x. At these walls, the potential energy of this particle will be infinity, because within the walls the potential energy of the particle may be constant, but it is for simplicity we consider it as 0, because the potential energy of the free particle is 0. So at these walls you can have these conditions. So when you substitute here, you will get the force exerted by the wall becomes finite value. Thus the potential energy of this particle at the walls becomes infinity. Thus we can define potential values of this particle outside the walls and within the walls of the potential well like this. Now you can write the Schrodinger wave equation for this particle along the one direction or one dimension like this: d square psi by dx square plus 8 pi square m by h square into e minus v into psi equal to 0. Between the walls the potential energy of the particle becomes 0. That's why this equation becomes d square psi by dx square plus 8 pi square m by h square into e into psi equal to 0. Now let us consider this term equal to k square, so that this equation 2 becomes a d square psi by dx square plus k square psi equal to 0. This is a differential equation. For this differential equation we can expect the solution like in this form: psi of x equal to a sin kx plus b cos kx, where a and b are the constants. In order to find a and b constant values, we need to apply the boundary conditions. Before applying this boundary condition, we need to define boundary condition for this problem. So this particle only moves within the potential well, within the rigid walls of the box, that cannot penetrate to this wall, that cannot stick to the wall, because when it collides with these walls, that immediately bounces back. So that the at these walls the probability of finding the particle is 0. That's why the wave function must be 0 at these walls. Psi equal to 0 at x equal to 0, psi equal to 0 at the x equal to a. These are the considered as the boundary condition for this problem. Now apply the first boundary condition to this equation 4, so that that equation becomes 0 equal to a sin 0 plus b cos 0. In this way you will get the b equal to 0. Now again we need to substitute b equal to 0 in this equation, so that that equation becomes a psi of x equal to a sin kx. Now for this equation we need to apply the second boundary condition. Second boundary condition is psi of x equal to 0 at x equal to 0, so that you will get the a naught equal to 0 sin k equal to 0, so that ka equal to n pi. You can write n equal to 0 1 2 3 so on, k equal to n pi by a you will get. Substitute this k value here in this equation here, so that you will get the en equal to n square h square by 8 pi 8 m a square, where n equal to 0 1 2 3 so on. If you substitute n equal to 0 1 2 3 so on, you will get the energy values in terms of energy packets, so that this particle can have only discrete set of energy values, so that we can say the energy of the particle is quantized, because it is a discrete manner so that's why we can say it is a quantized. Now we need to define a wave function of this particle. So in order to find a value, we need to take the help of normalization condition. Here what is the normalization condition? That is integral of psi square dx equal to 1, and we need to take limits for this problem, boundary problem also, so that here we have two boundaries 0 and a, so that we take the limits 0 to a psi x square dx equal to 1. Now take the psi of x value is a sin kx. K you can write it as n pi by a here, so that you can substitute in this formula, so that you will get the a value here, a equal to square root of 2 pi by a. Now substitute this value in this equation. Psi of x equal to square root of 2 pi by a, 2 by a, and sine of 2 n pi x by a. So this is a wave function of the particle enclosed in one dimensional potential well. Thank you.